make it a little bit more interesting than that and talk about TRAPPIST-1, which we found out about right after we submitted abstracts. So this goes right in with Ravi. And spoiler alert, I agree totally with what Ravi just said. 1E is the only planet I find that can be really Earth-like, so that's great to agree. This starts, is there? Fortunately, I can just skip all the habitable zone stuff. Jacob and Ravi gave excellent introductions to this. So is this not going to work at all? Go forward. OK, oops, too far. No. All right, and I'm going to jump right into what I'm going to be talking about, which is different climatic states you can have for these variety of different M-dwarf terrestrial planets. Kind of giving a little teaser to a bunch of the work on ProxN-b that'll be presented on Friday. This plot shows a different variety of evolutionary states that could happen around an M-dwarf because of its superluminous pre-main sequence phase. You can strip off a lot of the water and end up with different combinations of how much water and how much oxygen you have, to the point where Rodrigo Luger and Barnes and some other papers showed that you could have hundreds to even thousands of bars of oxygen, abiotically produced oxygen, on an M-dwarf terrestrial planet, even in the habitable zone, such as ProxN-b. So that is kind of a downer, but there's other potential states we could have as well. The work by Barnes et al. That's in review right now showed a bunch of different evolutionary states, and in the second paper by Meadows et al., we went through a bunch of these different planetary states that could exist around a habitable zone planet around an M-dwarf. And just to go through some of these really quickly, we believe we can find ways that you can have exo-Earth, maybe a little bit extra CO2 to keep it warm enough. You could have an early Earth-type planet. You could have one of these abiotic oxygen planets that we found from the evolutionary work. You could also have kind of these more evolved atmospheres, just like the oxygen one. If you did strip off the oxygen, you could also outgas CO2 as well, just like with Venus. And so you could end up with some kind of exo-Mars, like Peter Gao did some work in 2015 showing that if you have a very, very desiccated planet with less than 1 ppm hydrogen, you could have a planet that's in photochemical equilibrium between CO2, CO, O2, and some ozone. And then this planet, the recombination rate for CO2 would just be so low that you could have, again, another abiotic oxygen signature. And there's a couple others that I think Sunny Harman had touched on in an earlier talk. Then you could also have perhaps a planet that outgassed CO2 but also still had oxygen. And then you could even just have exovenus where the oxygen got stripped off but it outgassed CO2 later. And these, just for Proximus NB, and Vicky Meadows will talk a lot more about these on Friday, but you can even get a planet in the middle of the habitable zone with Venus-like temperatures. So going forward to what I'll be doing with TRAPPIST-1 here's just a kind of a little diagram of the models I'm using. A new 1D radiative convective model we call just VPL climate. And it does fantastic radiative transfer line by line, multi-stream, multi-scattering, everything, convection and condensation. We couple this with our photochemical model, Atmos. And it does all this stuff together, and what we do is we iterate the temperature profiles with the condensables and the photochemical species. So the climate model we start with provides the temperature structure, the mixing ratios we've assumed to begin with based on those earlier climatic states, and then also the condensable profiles. And that feeds into the photochemical model, and then the photochemical model is iterated to equilibrium, and then it can feed back the various constituents and how they've changed. And so these are iterated separately and coupled until equilibrium, until they're both in equilibrium. And then at any given point, then we have our converged state. And at any given point, we also can produce line-by-line transmission and direct imaging spectra, which in this session, we want to connect modeling with observation. So that's the observable is the spectra. If we go forward, there we go. So talking just a little bit about how the model iterates and its condensables. Here's just a snippet of runs. These aren't necessarily even the converged ones, but how we have a temperature profile on the left of an exovenus, such as TRAPPIST-1c potentially, and then the condensable mixing ratios of the actual condensate on the right. And you can see how as the model goes through several model runs, and it goes, the temperature profile varies until the dotted line was the last one. And the same thing here, we see how the mixing ratios change throughout the climate run. So we're calculating the condensables at every time step. And then we can prescribe the aerosols based on how much condensate mass is left, and then the radiative transfer routine can use those aerosols So going on to the results, which is what I really want to talk about. Before I go to those slides, I'm going to show a few transmission spectra. While the baseline values are different because these planets I'm showing are different sizes around the same star, they all have the same scaling of 200 ppm from the y-axis. And then I also show, which is the exciting part I think for the public, is what these planets would look like to the naked eye, to the human eye, observed from afar. Oh, sorry. Those will actually be the transmission spectra. I want to go through the climates first. And so instead of doing all 6 of those from that we talked about with ProxMB, with 7 planets to choose from and all these different climates, the model takes a long time. Only doing a few of the examples that are converged. Exo-Earth with extra CO2 like we talked about. And it's important to note too here that you get a 200-fold increase in methane, which I don't think has been mentioned yet. These M dwarfs, the photochemistry is very important, and you end up with a lot more methane, so that'll be an observable feature. We also do the exo-Venus with the sulfuric acid condensation, and then the abiotic ocean planets, or ocean lost planets that are completely desiccated at the end, so no water. And you get interesting temperatures. There we go. Again, we have the 1E, like I agreed with Ravi said about Eric Wolf's work. I also had struggled trying to make these warm enough. They would freeze over. I didn't try the maximum greenhouse type thing yet with those, but even once I got up to a large fraction of less than 1 bar of CO2, they were still frozen over. And then these went into runaway. Exo-Venus, these are hard, they're still running, but you get very hot, very hot temperatures. This is even a clear sky Venus. And some preliminary work we've done has shown that sulfuric acid may not even form as much around these stars. So you may end up with a clear sky Venus that doesn't even have sulfuric acid clouds. But for this case, with 4 ppm, this one does. And then, of course, the abiotic oxygen planet without water actually is much cooler. So you can get so-called habitable temperature, but not a habitable planet there. If this goes forward. I already gave the caveats about this. Again, you get eye color in the plot here. So this beautiful pale orange dot would be an exo-Earth. So it's not a pale blue dot like our Earth, and it's not a pale lavender dot like we found for ProxMB, which would kind of be like this color. It's still just reflecting the color of the star, which is roughly this color. And the important thing here is you get these pretty decent ozone features right here. You get whopping CO2 feature, which is going to be a feature of pretty much any outgassed planet. CO2 gives us that nice band there. And a bunch of methane and CO2 and water features are interspersed through here. And from the 0.1% methane that you get, you get substantial methane features. And if you look at the differences here, you get easily 50 ppm features across the board here and almost 100 ppm for CO2. So this is, I would say, definitely observable by JWST. And you even have other scientists. I know there's a lot of, cynical work about like, oh, it might just be 50 ppm. People like Drake Deming have suggested that you might get down to the photon noise floor of 1 to 2 ppm for JWST, which would be fantastic. And then you would see all of this. But even at 50 ppm, if we want to be pessimistic, you get the CO2 out. Moving on to the other ones, exo-Venus. This is like 1C, so this is very Venus-like. You can notice that, like many of the transmission spectra that have been taken by HST, for cloudy planets, you get a flat and featureless spectrum in the visible, and nothing important to see there. Other than the fact that you can see the transit height is so much higher in terms of the actual planetary structure. You're only probing the very upper reaches of this atmosphere, and we're not going to really know this part of that's not the observable, right? This is the modeler's side, and this is the observer's side. But you still get over 50 ppm of signal for CO2 in these fantastic CO2 bands. And that's really all there is there, except this V shape that Jada Arnes pointed out to me about sulfuric acid, which you'd say, well, okay, I don't know if there's really a V shape right there. This looks really flat. But when you zoom in on the data, then you can see that there is an actual like 2 to 4 ppm V shape centered at 2.7 microns in the near IR. So if we get down to 1 to 2 ppm noise floor in JWST, even this would be an observable feature for a Venus-like planet, which would be fantastic. And then my last atmosphere I simulated here would be the abiotic oxygen planet. And I think we've had a lot of talks in the session about CO2 and Earth-like planets, and so I get to talk about one that's really very different. You see this beautiful color. This is not just a pale blue dot. This is like a brilliant blue dot. significant ozone bands because this desiccated planet can't destroy the ozone. You get even 100 ppm features out of CO2, ozone, and even you get observable collisional-induced absorption features of oxygen. So these could be differentiated from each other by some of the various features, having the strong ozone, lack of water, lack of methane, in a desiccated planet. So in conclusion, I've shown that these climates are really dependent on the evolution of the star. The M dwarfs have a very superluminous pre-main sequence phase. This can desiccate the planet, it can strip off the atmosphere, or it could leave the atmosphere with some amount of water, depending on how much hydrogen the planet started with, and how much water you can actually retain. Or the planet could outgas, and so the composition of the planet then drives the climate, and this ends up giving us what the state is for a given planet's insolation. It's not just its position in the habitable zone. Any given position may have a variety of different states, depending on the evolution. And furthermore, TRAPPIST-1 will be a great example to provide us an opportunity to examine this evolutionary sequence with 7 planets, and I kind of skipped over that because I skipped the habitable zone part, but with these 3 planets in the habitable zone with 2 outside in the Venus area and then a couple that are really cold, we can really, if we can observe the TRAPPIST planets with JWST, this could give us a whole number of examples of how this evolutionary sequence might occur just from looking at the one stellar target. Thank you.
Great talk. So 2 questions. One, can you go back to your slide to where you showed the Venus spectrum? I think it went a bit fast for me to see the transit depth. How much is that transit depth?
This total thing is 200 ppm right here. So the differential is between 70, 75 and call it 70, 10. So it's 65 ppm-ish.
Okay.
So over 50 still for those. And this you're only probing 90 kilometers, which is the top of the cloud deck, basically.
Okay.
And that's 100 pascals there.
That's this is for a Venus analog. That's
yes.
what. Okay.
Yeah.
And well, we'll talk about that.
Sounds good. Yeah.
Great talk. In terms of the actual noise floor or what you can actually observe with wavelength, I'd encourage you to actually go online and run some of these sims on Pendex or another JWST calculation. You'll find that the MIRI instrument, which is beyond 5 microns, has broad bands, but not just the noise floor, but the overall sensitivity and throughput of the instrument is much poorer than the near-infrared ones. So your CO2 band at 4.5 or 4.2 microns may be much better for CO2 constraints or anything else. So I would really focus on shortwards of 5 microns, which there's a number of great bands in all of your models. And MIRI, yes, it appears from these plots as if it's the best, but if you focus on shortwards and actually run some calculations, you should be able to.
So my question to you, I guess, on that is in the Earth-like one, that could really, oops, I went too far. Could really help because these are strong bands right here, too, because of the methane. So those could be really great.
Yeah.
Good to know. Thank you. And I might add to that Jacob Lustig-Jaeger is going to be talking about spectral mapping and whatnot. And so that might be great too, to consider other ways of observing other than spectra.
I just have a quick follow-up to what Avi was saying. Would the broadness of the features help in the MIRI band if the transit depth is below 50 ppm, would the broadness of the features will help? So for example...
That could, because the CO2 band gets so large that you get a strong signal over a large wavelength range. So even at coarse bands, potentially.
Your integrated depth is half of what you see because of the slopes.
Yeah. So if you had a box here.
So I'm going to talk on Friday about actually using phase-dependent thermal emission to go after things like CO2 because it is so broad and we can use the MIRI bands for that. So that's a different way of getting at this.
We have time for one quick question, Stephen.
This is quick. Thanks for a great talk. So given the uncertainty on the bulk densities of the planets from the transit time variations, how sensitive are the convergence of your models to those bulk densities, and did you try a range within the uncertainties of those?
I've not tried a range for each planet. I just essentially took the nominal value. And there are, you said the error bars are huge on the mass. That definitely changes the scale heights. And so that would certainly affect some of these results. What I found is that applying these same atmospheres to each planet, the ones that can converge, the climate states are relatively robust amongst the different masses of the planets. So doing like D and E and getting consistent temperatures, given the fact that the insolation is lower for E, for example, the climates still show similar things.
Okay, thanks.
Let's take Andrew one more time.